Welcome. We are in Unit 1, Arithmetic and Algebra Essentials, and today we do our second lesson. Focusing on this section R2, Algebra Essentials, we'll cover 4 objectives. We will graph inequalities, find distances on the real number line, evaluate algebraic expressions, and determine the domain of a variable. So our first topic, graph inequalities. Well, here are 3 inequalities. X is greater than -5. Sometimes you might say x is strictly greater than -5. X is greater than or equal to -5. And -3 is less than x, which is less than or equal to 7. And for each of these, what I'd like to do is look at the number line and mark up the number line somehow to represent these inequalities. So let's take a look at the first example. X is greater than -5. So starting at -5, I mark up, I shade in the number line for anything that's greater than -5. The real question comes, what do I do at -5? And what we do is we're going to put a parenthesis there. And the parenthesis indicates that I don't actually include the -5 itself. Now, in the second example, again, I'll mark the number line, everything to the right of -5. But I do want to include the -5 among the possibilities because x could equal -5. In this case, we use a bracket. Now, the language is important here. When you have a rounded end, this is a parenthesis, and when it's squared off, that is a bracket. And so use the proper word to describe what you really mean. Now, in this last example, x is caught between two values, -3 and +7. So we can shade in that region, but I don't want to include -3, so it gets a parenthesis, and I do want to include +7, so it gets a bracket. What if we go in the opposite direction? I start with the 4 graphs. Can you figure out what the 4 inequalities are? I'll give you a second. Let's take a look. All right, first picture. X is strictly greater than -4. How about the second one? X is less than or equal to -4. The third, X is less than -4, strictly less than. And in the last example, X is greater than or equal to -4. All right, moving on to our next topic. Distance on the number line. So on a number line, I might mark 2 areas, 2 numbers, say -3 and +1. We'll call those A and B. And I ask, what is the distance from A to B? Well, it's pretty obvious. I can count 1, 2, 3, 4. There are 4 units from A to B, so that distance is 4. And I say that, the distance from A to B is 4. And we could go in the opposite direction as well. The distance from B to A is 4. It doesn't really matter. Mathematically, how we denote distance is with a little d. So this notation, d parentheses a comma b, means the distance from A to B. And if I switch the A and the B around, the distance from B to A, obviously it's still 4. Well, what if I want to actually calculate with numbers, like the -3 and the 1? In this situation, we use absolute value. In fact, this is the reason absolute value was invented, is to show distance on the number line. So the distance from A to B is going to be absolute value, A minus B. All I need to do is put those 2 numbers in there and take their difference, and the absolute value is going to show me the distance. All right, let's give that a try. So -3 and +1. I'll compute the absolute value of -3 minus +1. And let's see, -3 minus 1 is -4. So that becomes the absolute value of -4. And the absolute value of -4 is just 4, like we expected. The answer is 4. And if I switch around those 2 numbers, let's take the absolute value of 1 minus -3. Well, let's see here. 1 minus -3 is the same thing as 1 plus 3. So that's the absolute value of 4, which is just 4. So it really doesn't matter which order you put the -3 and the 1 in. In both cases, you'll get 4 out as your answer. So absolute value helps us figure out distance. Okay, topic number 3, evaluate expressions. So just a quick word about terminology here. Expressions are things like 2x minus 1, a plus b plus c, 34 minus 9. Sometimes students get these mixed up with equations. Now, equations always have an equals, not there, always have an equals sign. So when you see an equals sign, it is an equation. If you don't see an equal sign, do not call it an equation. It is merely an expression. Okay, so I have these expressions, and I want to evaluate the expression. So to evaluate basically means just turn it into a number. Give it a value, right? To evaluate, make it a value. So in this situation, if x is 5 and y is -1, I'll substitute 5 for x, and I'll substitute -1 for the y. I like to put parentheses around the numbers that I'm substituting in just to help set them apart and visually see what's going on. So that looks like 5 plus -3. 3 times -1 is -3. And then 5 plus a -3 is the same as 5 minus 3. And that answer gives us 2. There, I have evaluated that expression at x equals 5 and y equals -1. Here are a few more examples. Maybe stop the video for a second and see if you can figure these out, and then start when you want to see the answers. All right, I'll go through the answers now. Let's see, I'll evaluate 5. Now x is 3, y is -1. So 5 times 3 is 15, so it looks like -15 is my solution. In the second situation, I substitute -1 for y, and I substitute 3 for x, and the numerator becomes -3. That denominator is 2 minus 6. So that's -3 divided by -4. I have negative on top, negative on the bottom. So it's like a factor of -1 in both places. I can cancel my factor of -1, and I end up with 3/4 as my solution. Lastly, for x is 3, y is -1. 4 times 3 is 12, and subtracting a negative is like adding. So this becomes absolute value of 12 plus 1, which is the absolute value of 13, and the absolute value of 13 is just 13. There we go. All right, let's move on to our fourth topic, the domain of a variable. We're continuing to think about expressions, so consider the expression 1 over x. We might ask ourselves, what kinds of values can I put in for x? How can I evaluate this thing? Now, I could put in 2, and that gives me an expression 1/2, which is perfectly fine. I could put in something like -17, which gives me 1 divided by -17, and that's okay. That's just the number -1/17. But there is one value I cannot put in, and that is 0. Do not do this. All right. In math, we are not allowed to divide by 0. Never divide by 0. So we often have an expression and we ask ourselves, what values can x take on? What's it allowed to be? What values can x assume? And in this example, x can be anything except 0. And so we say the domain of x is any x such that x does not equal 0. So this is kind of using set notation, kind of the fancy mathematical way of saying that. The trick is when you get to that vertical bar, that's when you read such that. So the domain is any x such that x does not equal 0. Here's our definition of domain, the set of values that a variable may assume. That's what's called the domain of the variable. One more small example. What's the domain of x in this expression, 34 divided by x plus 10? Do you see that? Well, all I know is that this denominator may not equal 0. X plus 10 may not equal 0. Oh, so what does that tell me about x itself? So x is not allowed to be -10. So the domain of this expression, the domain of x in this expression is any x such that x does not equal -10. There we go, and that's the solution. Just a few more examples of this domain problem. 4 expressions, and I want to find the domain in each of the expressions. Pause the video if you want to give these things a try, and then start up again when you're ready for the solution. In the first example, x is in the numerator. And a lot of people think that 0 is a problem. Certainly other numbers aren't. I can do 1 divided by 24 or negative 17 divided by 24. Those are all perfectly fine. 0 divided by 24, is that allowed? And the answer is yes. 0 divided by a number is okay. That's just, the answer is 0. I'm just not allowed to divide by 0. So in this particular case, in problem number 1, in fact, the domain is all real numbers. There are no restrictions on x. So I might just write the domain is all real numbers. All real numbers. Okay, how about example number 2? Well, x in the numerator doesn't matter. In the numerator, it can be anything, so I don't care. All I really need to do is focus on the denominator. And I see that x minus 24 may not equal 0. Oh, so that tells me that I guess x itself is not allowed to be 24. So I think the domain is any x. Any x. I can put any x in there I want, with the exception of 24. Any x such that x is not 24. All right, problem number 3, continuing as before. Let's see, x squared minus 9 may not equal 0. So in other words, x squared is not allowed to be 9. Now this is interesting. There's actually a couple solutions to this, right? Squaring x, x can't be 3, and x can't be negative 3. In either of those two situations, if I squared it, I'd end up with a positive 9. So in this case, we might write the domain as any x such that x does not equal 3, and, it's okay to just write the word and in there, x does not equal negative 3. There we go. And I'm using braces. My set notation uses braces. Last question, number 4. As before, I look at the denominator, and I see x squared plus 9 may not equal 0. But then, wait a second. I mean, is that even possible? I mean, is there any x that actually makes this thing equal to 0? If there were, I'd have to have x squared does not equal negative 9. Well, that's true for all x, right? Whenever I square a number, it's always going to be either 0 or positive. There isn't any real number I can square to make it equal to negative 9. So in fact, my domain, just like in problem number 1, the domain is all real numbers. Now, in some other courses, you might talk about complex numbers. We're not going to worry about those for now. We're only going to restrict our attention to real numbers. And there is no real number that could make that denominator 0. So the domain is all real numbers. Any number works. All right, so we have talked in this section about graphing inequalities, distance on the number line, expressions and evaluating expressions, and then the domain of a variable in an expression.